the fundamentals of ECG. It's, of course, you learn it, what is the electrocardiogram and what it does. Basically, it's recording the electricity or the changes of the potential differences in the heart. Okay. Now, this doesn't show the exact function of the heart. It's only showing the electric activity. And of course, it's proportional how the heart works, but it's not identical. This is, you have to keep in your mind. Okay. This is, you learn very well that what the bipole is made, but it's very important. ECG recording changes. These changes, that's meaning that when the electric bipole is somehow is generated and is changing time by time. Very, very important that usually this is a vector that we are recording. So the positivity is recorded when the charge is goes toward the electrode. If it goes away, that's be negative. That's very important one. Okay, such as here, for example, as you see, when it's going toward electrode, it's positive. When it's going away from the electrode, that's be a negative charge. This is the important one. Now, this is why when we measuring the electric potential differences and we are putting on the electrodes on the patient, that's going to be changes of the, and different lead give you different charges. Now, every impulse that is made is coming from the endocardium and goes toward the epicardium. And this is why we do have a positive deflection detected over the part that the charges goes. Okay, this is the depolarization at the beginning, and after very slowly, that's going to be the repolarization that goes exactly the opposite way. But so it's meaning that the repolarization is started in the epicardium and goes toward the endocardium. So relatively less time is spent in the epicardium, and the repolarization goes exactly the opposite way, but because the charge is exactly the different one, this is why we do have detect a positive deflection for the repolarization as well. Now, if you are comparing the action potential in the epicardium and the endocardium, you can see that the epicardium is ending first, and the endocardium, the action potential, is wider, the plateau phase is wider. This is why this repolarization be the opposite way. Now, what is the good for the ECG? Basically, it's a non-invasive evaluation. That's good. Fast and very wide available right now. And the registration is inexpensive. And however, sometimes it's very good a diagnostic value. However, sometimes it's not. And of course, you have to be trained to solve this problem. So there are some advantage and disadvantage of the ECG, but you can gain a lot basically because that's a non-invasive and very fast measurement that we do have. Now, ECG cannot use for everything. Basically, if you are looking at the best for ECG is the arrhythmias. Arrhythmias can be diagnosed very nicely, especially we learn it later on that the arrhythmias is categorized first of all based on the time and based on the origin of the arrhythmias, and the ECG is good to detect where this arrhythmia is formed and how it comes. But some other way is not so good. For example, in the ion alteration, we do have the lab values. It's much better to use the lab values than the ECG itself. Now, anatomy, I don't want to talk too much about, but one thing that's very important, the SA node that has a nodal tissue that generates that's a pacemaker that generates the impulse that propagates to the atrium and reaching the AV node. Here we do have a little slow down, and after we do have the bundles, and that is very fast conducting pathways. And after the Purkinje fibers, and this activate the ventricle. So this is what we do have action potential tissues. Okay, it's different one. We do have this is the pacemaker action potential. This is the depolarization what we do have. And after depolarization, this is how the nodal tissue works. That's the nodal tissue. If you compare the nodal tissue to the muscle, that's completely different one. The muscle, when the sodium flows in, it's very rapid one. We do have the plateau phase where the contraction taking place. And as you see here, the tension highs develops, and we do have the repolarization. You can learn this one very well, and especially if you're not using it. Now, based on the different sequences, first the atrium is depolarized. This is what we have. We do not see the sign of the SA activation. We do see the whole atrial activation only. Now, when the atrium is activated and when the charge goes through the AV node, to the AV junction, relatively we are not detecting anything. When the ventricle is activated, this is what is called the QRS complex. You learn it. And when the whole ventricle is depolarized, we have nothing. And when the repolarization is starting, we do have the T wave. And of course, between the next P and after the repolarization, we do have a little lag period. Especially this lag period is very important because this is where the coronary circulation taking place. So this is how the heart can get some oxygenation. ECG placement, you should know it very well. That's Einthoven and horizontal leads. So basically, we do have some bipolar leads and we do have some unipolar leads. Bipolar ones, such as the Einthoven leads between the right and the left arms and the foot. And this way, we do have a number one, number two, number three, and the Wilson unipolar leads when we do have the absolute zero and compared to the right arm and the left arm and the feet, this is the foot, and this is how we do have this augmented. This is augmented because we have to amplify a little bit. The amplification means that they are taking out this resistance, and this is how they're recording a little bit bigger voltage. The chest leads unipolar all the time is unipolar. It's placing from the right sternum and all the way the axial area in the V6. And sometimes they put some other in the right side. We will talk about, especially when we do have the oxygenation abnormality, and you will see those. That's a 15 leads ECG, but generally we are using the 12 leads ECG. It's enough basically for us to diagnose. This is the placement. I don't want to talk too much about it. Okay, you can read it and you already watched it. Okay, electrocardiogram. Again, how it's made, what the action potential and how the action potential is translated to the QRS complexes. And this, again, you can watch it. Now, terminology is very, very important because when we are talking about, for example, the ventricle activation, depending on the lead, you can have different shape of this QRS complex. And this is why we do have a general terminology. And this way you have to learn it. Every positive deflection in this ventricle activation is called the R wave. Okay, so every that is positive, that's an R wave. The first negative wave before the first R, that's called the Q wave. Depending on the size of the wave, we do have a small caps or capitals. Okay, this is how you label the size or the voltage. So if you do have a big R wave, that's a capital R. If you do have a small R, that's a small caps of the R. Now, every negative wave that follows, which after the first R wave is called S wave. We can have more R and more S wave, but we have only one Q wave. So for example, this one is a small R and a capital R, and between we do have an R. So this is an RSR complex that we call. Here we do have a RS or RS complex. If you do not have any initial R, that's a Q wave, but because it's too deep, this is why it's called the QS complex. That's a Q wave. That's be a pathological Q wave, but in some leads, we can have this complex. This is a QR complex, and that's a deep Q, so this is a capital Q and R complex. Okay, let's look at the activation of the ventricle. Basically, at the beginning, we have nothing. However, because when the septum starts to activate, the septum gets the impulse from the which bundle gives it to the left bundle. So it's me, everything is goes from the left to the right. Okay, so this is why the septal activation initiates a positive little R deflection in V1. However, in the opposite, in a V6 that, let's see, looking at the left side gives a negative, or it's a Q wave, a small Q wave. So this is what we do have as a septal activation. Now, what will happen after that the bundles and the Purkinje fibers activates both ventricle, the right and the left one, but because the left one is thicker, when electric activity is about 5 times or 10 times higher than the right one, this is why you do have a positive deflection in V6 on the left side and a negative deflection on the right side because everything goes away from the right side. This is how we do have this kind of activation, and this is how you can explain what's happening in V1 and V6 on the right side and left side. In the chest leads, you can see very nicely, and the limb leads mostly detecting the left side. So, for example, lead number 1, lead number 2, AVF, and AVL is a left ventricular leads as well. Okay. And now here what we do have, if you are seeing that this kind of pattern is converted to this pattern. So from V1 to V2 continuously what we do see, the initial R is getting bigger and bigger, the S is getting a smaller one. We do have a transitional point that between V3 and V4, and usually the biggest R detected in V5, or depending, of course, the size of the or the place of the ventricle, and this is high then. You have to know this kind of reference values by heart. That's important because when we evaluate the ECG, we have to know it. And because every portion of the ECG means something, and we want to evaluate it. Okay, now ECG is very good to basically estimate the heart rate. Well, when we are looking at, for example, the pulse, we can do the heart rate much better way. Now, because ECG is a very fast one, because the speed of the paper or the chart is about 25 millimeters per second, relatively it's very fast. And if you do see that about 5 squared, we do have this within 1 second. So this is what we are going to evaluate. And another one, the voltage is meaning that 10 millimeters reverse the 1 millivolt. This is how you can compare or how you can calculate it. Now, the estimation of the heart rate, that is two things. You do not need to have the exact heart rate because nobody cares about the exact heart rate. You want to know is it normal one or slow one or faster one. This is what you have to do it. Now, you can use the distance between two R waves, especially when we do have rhythmic heartbeats. Okay, now you can calculate it, but we are not measuring in time because it's very, very difficult, especially it's difficult to divide, like, for example, 60 by 0.96. So it's almost impossible to do this one. This is why we do have an estimation. Now, what the estimation means? The estimation is a very simple one. You know that if we do have 5 boxes, it means exactly 1 second. If you do have a beat that comes in every second, for sure the heart rate is 60 beat per minute. If you do have 1, it means 5 times faster than 60, this is 300. If you do have 2 only, that means 150. If you have 3, it's the 1/3 of these 300, so 100. If you have 4 squares, it's meaning that half than the 2 squares, so 75. So this you can estimate it. Or simply saying that the heart rate should be calculated based on the big squares, 300 divided by the number of the squares between two R's, and that's it. Now, as you see here, the normal is falling between 100 and 60. That's the normal range for the heart because the rate is not the same in all time. So you can be very sure if the RR intervals is between 3 and 5, you can say immediately normal. And because you cannot use it for any other reason to figure out that it's 75 or 80 or 90, doesn't matter. It's normal. Okay, this is what you have to know it. So basically, you have to memorize this one that from 3 to 5, that's a normal range. And if it's longer than 5, that's bradycardia. If it's faster than 3, tachycardia. That's it. Nothing else. Okay, this is what we already said it. Good. Now, what is the heart rate here? Now, let's see here, for example, 1, 2, 3, 4, 5, 6. So, and a little bit more than 6. So it's about 300 divided by 6. It's 50 beats. Fine. You can calculate it. What is the rate here? When we calculate the rate, we calculate the QRS complexes, the distance between the QRS complexes. You are not calculating the atria. We will see that's an atria flutter. So, of course, the atria one is faster than a ventricle one, but you can see this 1, 2, 3, 3 a little bit more. So it's so atrium goes about 300 beats, but the ventricle is slower because, as I said here, we do have at least 3.5 bucks. So it's meaning between 175. Okay, 175. So it's close to 75. And we can say maybe a little bit more than a little bit less than 75 or 70 or 72, doesn't matter. Now here we do have these big complexes. This is a ventricular flutter. We will learn it. So that's very fast. And if you do see it, about almost 2. So it's 150, but faster than 150. So about 200 beats per minute. So we can calculate it. Okay. Now, what's happening when we do have an irregularity in the written? So the RR interval is not the same. Well, we can do the same when we calculate the pulse or when we measure the pulse. We cannot measure the pulse for 1 minute or 30 seconds, but we can measure to, for example, at least 6 seconds. And if you measure how many R waves you do have in 6 seconds, you can calculate very simple one because you have to multiply by 10 if you calculate it with 6 seconds. If you measure for 3 seconds, you have to multiply by 20, and that's what, that's what. If you calculate for 15, you have to multiply by 15. It goes, and very good. This is how you can do it in an irregular or regular rhythm as well, so you don't need any problem. Okay, this is what I already written here. Okay. Now, electrical axis. Electrical axis, why do we need the electrical axis? Basically, the electrical axis is used to determine how much time is spent to the left side or right side, or what kind of sum of the axis can be substitute the moment and axis. Now, as you learn it, the normal axis is ranging from 0 to plus 90. Okay, everything is positive on the normal side, so between in this below, and negative is up. Now, normal range is from 0 to 90. That's meaning that the anatomical axis of the heart is about the same than the electrical axis of the heart. It's a normal position. However, if you do have an extremely deviated to the left or the right, for sure anatomic situation cannot explain this. So you do have some kind of conduction abnormality or some pathological condition in the heart. There are some other portion, for example, the simple left deviation or simple right deviation. That means there are some situations that a patient can have this kind of axis deviation, such as, for example, a very obese man can have because the diaphragm is pushing up the axis of the heart, and this way they can have a left deviation. Or somebody is a tall one and skinny one that can have a younger one, especially can have a right deviation. So that can be normal, but it can be pathological as well. You have to diagnose or compare the situation with the patient in this. Okay, now How can we determine the hexaxial system? The best one to use is we use and translate these Einthoven triangles or the limb leads or the frontal panel. The frontal panel is used to diagnose the electrical axis. Now, I explained well in the video that, and you already learned how the hexaxial system works, so nothing else happening. Basically, every vector is pointed in the one position, and after this is how it's named. And if you are looking at the different leads here, if the action potential goes away to that lead, you will detect the highest deflection in the certain lead. Now, another thing that can happen, the quadratic approach of this electrical axis, we will go through the examples and you will see it nicely. So basically, if you see this is mostly positive, you're not looking at only the R wave, only the positive wave. You have to subtract the negativity out of the positivity, and this is what you will put on the axis. This is how you detect it. This is mostly positive, this is mostly negative, and that's equiphasic. It's meaning exactly perpendicular to that certain lead that we do have. Okay, nothing else what the new is. So let's look at and let's start to evaluate an ECG tracing step by step. This is how we start. Of course, we cannot do everything today, and this is why only what you learned in the fundamental, this is what we are doing it. When we are looking at an ECG, a tracing, the first thing that we have to look at, whether it's rhythmic or not. You don't need to care anything else. You have to look at the interval, or you have to look at by an eye how this RR interval is placed. Okay, for the first view, it looks like rhythmic. Of course, if somebody looking at, for example, that beat, that a little bit small the distance between these two, so that's possible. It's a arrhythmic a little bit, but compared to what you will feel if you feel the pulse of the patient, possible you see nothing else, you will feel rhythmicity. Okay, so I would say that this is rhythmic. Okay, next one, we're still looking at the ECG. What is the next one? Next one, we have to calculate the heart rate. Okay, how do we calculate the heart rate? The one possibility, we can use the 300 divided by the number of the square. Okay, so let's see, 300, all right, divided by the number. Let's see. Okay, it looks like 1, 2, 3, 4, 5. So it's divided by 5. That's simple one because it's meaning that this is exactly 60 beats per minute. That's fine. Good. This is what we can use. Okay. And another possibility we can use it, okay, as I said, the last one, what we are using for this arrhythmia. Let's count how many beats, simple to the past, how many beats we have, for example, how this is 1 second, 2 second, 3 second, 4 second, 5 second, and 1, 2, 3, 4, 5, okay, 5 seconds, 6 seconds, okay, this is 6 seconds, okay, sec. How many beats we have? 1, 2, 3, 4, 5, 6, 7. See, 7. If we had 7 in 6 seconds, 60 seconds, we have 70. See? So that's meaning that this is closer to the real because this portion, what we had here, was arrhythmic. So you can use this one. But does it matter whether it's 60 or 70? No, because we say that's normal. That's normal. So nothing. Okay, let's go on. What is the next one? The next one, of course, we don't know right now, but looking at the QRS complex, do we have a P in front of the QRS complex in everywhere? Yes, we do. And by looking at the position and the shape, especially in lead number 2 is positive, because lead number, the P wave is originating and giving the impulse from right to the left. Okay, so if you are looking at a heart, for example, this is a heart. Okay, so everything starts in an SA, all right? This is an SA node, and the atrium is activated this way, yes? So it's meaning that if you are looking at, for example, the hexaaxial leads, what we have here, okay? All right, this is, I would say, this one, AVL and AVR. No, I put every leads there. Okay, so lead number 1, lead number 2, this is lead number 3, I forget it, lead number 3, and AVF, AVL, and AVR. Okay, now, in those leads, when the impulse goes toward the leads, it should have a positive deflection. So 1, 2, AVF should be positive, and AVR negative. Yeah, this is positive, and look at AVR is negative. Okay, so this is a sinus rhythm. This is one thing. And another thing, because it's rhythmic. So this we have a sinus rhythm. And because it's rhythmic and because the P and the P wave is always the same and the heart rate is normal, that is a sinus rhythm. Okay, now let's look and let's go. No, no, no. I'm going and I'm going to erase this part. Okay. All right. Now, what is the next one? The next one, basically, now we will later on practice with this one, the shape of the P wave, the PR interval, the duration of the QRS, and so on and so on. But now let's concentrate on the axis. Okay, let's concentrate on the axis. It's meaning that the ventricle activation, when we do have a small portion, a momentum vector, when it's summarized, how does it look like? Let's look at how can we estimate the axis? No, tell me, how did you activate the axis, Caroline? I'm waiting for your typing. Okay, let's see which lead that we do have, positivity and negativity. Lead number 1, positive. Lead number 2, positive. Okay, quadrant method is very good one. So what does it mean, the quadrant method? Basically, the quadrant method is meaning that you want to figure out where the axis is located. First, you have to look at lead number 1. Lead number 1, it will tell you, I will change the color, it will tell you that which half the axis is located. If lead number 1 is positive, it's meaning that you are on the left side, yes? Okay, very good what you write. So we are on the left side. Okay, that's very good. The next one that you should look at, this is AVF. AVF is positive at the bottom, okay, this half, but the common part should count, and this is the easiest way to look at it. So you are between 0 and 90, so you have a normal axis. Good, very good. But let's see more accurately what the axis is. Um, you can look at in every case, you can look at in every lead and do this kind of half, and that's a common part B. For example, lead number 2 is positive. Okay, lead number 2 is positive. Okay, because that's a 60. Okay, that's 60. All right. And exactly perpendicular to minus 30 and 120. That's fine. But we cannot get more out of it than using only zero lead number one and AVF. Okay, let's look at other lead, AVL. Okay, AVL. Let's look at AVL. AVL a little bit positive. Okay, where positive the AVL is? Okay, in this portion. Okay, in this portion. That's all the way positive. So I would say that now, because it's positive, we are between 60 and 0. However, because it's almost zero, it's meaning that it's very close to lead number two, because lead number two exactly perpendicular to AVL, and that has to be 0 in this portion. But because it's positive, we can get a little bit further up. So we substitute minus 10. It's meaning that the axis is around 50. Okay, 50. Now, we will go on and we will explain later on how does it work if you did not understand, but this is how it goes through the all ACG, I mean this axis determination. Okay, let's look at the next one. Good. Now let's see. First one, rhythmicity.
Uh, if you see lead one and two, the P waves are always preceded
Okay,
before.
but first the
uh,
rhythmicity. First the rhythmicity. It's meaning that's rhythmic. Good.
yeah, it's
And
rhythmic.
okay, every QRS preceded with a P wave. That's
Yeah.
good. It's a sinus written. Good. So far, this is what we are made. Next one, the heart rate.
If you see there between two R waves, there are about four squares, four large squares, so it can be 75 beats per minute.
Okay, but if you look at this one, it's a little bit more than 4. So
Yeah.
it's meaning, doesn't matter, but it's meaning a little bit less than 75. So it can be 72. That doesn't matter. Okay, doesn't matter because it's a normal. You can see immediately normal. All right,
Yes.
normal. Okay, it's about 75. Good. Next one. Now the axis that we are doing.
If by the quadrant method,
Okay,
both lead one and AVF are positive.
okay.
So
One is positive, AVF is positive. So immediately you can say it's a normal. Yes?
yes, and also by the equiphasic method, the lead one is most equiphasic, I think.
Uh-huh, uh-huh. So it's meaning that the positivity and the negativity is equal. So its meaning is 0. So what does it mean? This is lead number one. And what is perpendicular to lead number one? AVF and
AVF
this portion. But because this is in should be the negative range, so AVF should be negative here. But because AVF is positive, so the axis is
is
90
yeah
degrees. Yeah.
plus 90 degrees.
That's it. Good. Very good. Okay. Thank you. Okay. I hope we can go to the next one. 103. Who has 103?
Good morning, it's me.
Okay. Good morning.
I can try sharing my screen. I'm trying.
Good.
Can you see this?
Wow. All
So
right.
I just annotated it step by step. So I
Good.
guess you can see like the different numbers that I've done, but I'll just start. So
Can you
because
magnify it? Can you magnify
yes,
it? Please
I
magnify
will
it. I think it's a
try.
control and a roller on the mouse. Yeah.
Is it better like this?
Yes, 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 yes.
Okay.
Because, okay, now you can explain it.
Okay. So first of all, we can see that the P wave in lead number two is positive and the P wave in AVR is negative. Therefore, we can say that we have a normal sinus rhythm. And we can also see that just by looking at it, that the QRS complexes are appearing in a rhythmic way. So they are regularly spaced out. As for the heart rate, we have approximately 2.5 large boxes between the RR intervals. So we can divide 300 by 2.5, and then we get roughly 120 beats per minute, which is the ventricular rate. We can also do it in a different way that you've said, where we would calculate how many QRS complexes we have in the different seconds. So if we have in 1 second 2, then we can multiply that by 60, and then we get also roughly 120, which
Mm-hmm.
I would say is mildly tachycardic.
No, no, no,
Uh,
you don't need to say mildly or a little
just
bit.
tachycardic.
Tachycardia. That's it,
Okay, okay.
tachycardia.
And we can also see, I know this was, you mentioned in your videos that we can see atrial flutter when we have some irregularities in the P waves. So I also put that there. I'm not sure if that's
No, no, no,
accurate.
because you've written very nicely that, for example, I'm making some notes on it. So
Hmm.
this is the T wave that you put it in very nicely, and this is the P wave, okay?
Hmm.
So this is not a flutter wave because in the flutter wave, when we do have an atria flutter, this is how it
Hmm.
looks like. This is a saw, okay? And
Okay.
every wave, this represents an atrial depolarization. And here what you do have, there is no, the discrete atrial depolarization, you have a P wave, okay? And this is not a P wave, this is called the flutter wave, the F wave. We will learn it the next time, don't
Okay.
worry.
Okay. And yeah, I basically after that just yeah, we can also see that the QRS complexes are narrow.
Mhm.
And then I also just calculated the intervals. So most of them are normal. I think the QRS is a little bit over 0.11 seconds. It was 0.12, but I mean that's not huge
That's okay.
difference.
That's okay. Because look at here, if you stick to lead number two, maybe you found that a little bit bizarre, but no. If you count how many squares, small squares we have, 1.5 or so. So I
Yeah.
do not think that is too much. And especially if you
Mhm.
come here in V2, V1, that's completely narrow QRS complex. This is not wide. If it's wide, believe me, it's meaning that we look at this is exactly zero point 0.2 seconds. Okay, this is zero
Mhm.
point 0.2 seconds. So it's, and if you do have a QRS that at least more than 3 squares, the 3 millimeters, now that's wide, but this is
Okay.
not wide. Okay,
Okay.
all right.
Yes, so the intervals, and then after that, I just went on to the axis
Hmm.
determination.
Hmm.
Hold on, let me this. So we can use, of course, both approaches. Maybe I'll start with the quadrant approach because that's more of like the approximation.
Hmm.
So
Easiest one.
lead number one is positive. As we can see here, it is mainly positive. And so we place it on the left side of the hexaxial system. And then we look at ABF, which is also positive. So we're going to place it on the lower quadrant. And then,
Hmm.
as you mentioned previously, the intersection of the two will give us angle or the QRS axis between 0 and positive 90 degrees. So we know
Okay,
that is normal QRS
okay,
axis.
good.
And with the equiphasic approach, I found AVL to be the most equiphasic of these leads.
Well,
Um,
still positive, but
yeah,
it's okay.
yeah. And so the lead that is perpendicular to that would be lead number two, which is positive. So I would say the angle is around 60, positive 60 degrees.
Okay, now I give you an other easy way to determine the
Mm-hmm.
axis. Okay, so we agreed that everything that when the electrode goes, well, goes to not the electrode, the deposition wave goes toward the electrode, that's be positive. Yes, that's be
Mm-hmm.
positive. Okay, let's look at lead number one. Let's look at lead number one, lead number two, lead number three. Choose the biggest one. Which is the biggest one?
Two.
Okay, so it's meaning that the axis is close to what you said, 60, yes?
Yeah.
But if you had 60, it's meaning that you are exactly in the middle of lead number one and lead number three, exactly 60, 60 degrees. Yes?
Yeah.
Okay, but because you do not have the equal positivity in lead number 1 and lead number 3, what you can see, lead number 1 is bigger than lead number 3. It's meaning that you are a little bit toward lead number 1. This is what you see. It's about 50, so minus 10 degrees, about 50.
Okay.
And that should be, which one? Oops,
It's 104.
104. That's it.
Yes.
Okay, good. Now it's your turn.
Yeah. So for the heart rate, I did
First, rhythmicity. All the time, rhythmicity. Is rhythmic or not?
it's not.
Good, very good. It's not rhythmic because you can see here that the RR distance is changing, is getting smaller and after getting longer again. Okay? We will learn it. That's a physiological arrhythmia, so that everybody could have it. Okay?
So
Now,
I took the first 3 seconds and counted
let's
to
see.
50.
1, 2, 3.
So there is 4.
Okay?
So 4 multiplied by 20,
Mhm.
it's 80.
Okay, good. Now, if you go a little bit further, for example, here we can see 1, 2, 3, 4, 5. Okay, 5 means you have to multiply by 12. Okay, and how many we have? 1, 2, 3, 4, 5, 6. So it means it's about 72. Longer time gives you a more accurate value. If you count only for, let's see, 2 seconds, see, for example, 2 seconds, you have to multiply by 30. It means 3 times 30 is a 90. So this is, if you want to use this kind of method, it's better to use a longer interval, as long as you could. Okay. All right, go on, but doesn't matter. Does it matter? No, it's normal. Good, go on.
And for the axis, I use the equiphasic approach. Lead 1 is the one because
Mhm,
it's like the 0. Um, so it's between minus 90 and 90, and
mhm, mhm, mhm.
AVF is positive, so the result is 90.
Mhm. That's it. Correct. Good. Very good. Very, very good. Thank you very much. Okay, the next one. Huh? I have to check it. Wait a minute. Stop sharing. Maybe it's not here. Oh boy. Oh, yeah. I'm sorry. So 105 is Hussein. Possible is not here. Yes? Okay. I check it. Okay, Hussein. But maybe he's okay. Not here. Doesn't matter. We will go through. Okay. I'm going to guide you through this. Okay. So, for example, what is the first one? Rhythmicity. Is it rhythmic? No. Again, this is not rhythmic. And especially if you go here, you can see that we do not have the same kind of positive P waves. So it looks like that the P is changing. So it's not a sinus rhythm. We will learn later on. Okay, so it's because it's a rhythmic one, we have to do the average. We have to average the heart rates. Okay, how many seconds we have? 1, 2, 3, 4. 4 is meaning that we have to multiply by 15 to make it 60. Okay, now 1, 2, 3, 4, 5, 6. So we have to multiply 6 by this one. So that's about 90 bit per minute. Oops, I cannot write it. Okay, so 90 bit per minute is still normal. Now let's look at the axis. Okay, let's look at the axis. When we do have this kind of arrhythmia, especially we will learn later on that this is a supraventricular arrhythmia. So you can calculate the axis because the ventricle activated the same way, almost the same way. So we don't have any abnormalities. We can use the quadratic approach first. Lead number one is positive, AVF is negative. What does it mean? It's meaning that we are up here. Yes, we are up here because AVF is not positive. Okay, so which is the next lead that we have to look at? The next lead is lead number two. Lead number two, because lead number two, I'm using a different color. Lead number two is going to be perpendicular to -30. Okay, this is what we are interested. And this is all the way, this is positive. Okay. And on other side of it, it should be negative. So that's positive in lead number two and negative in lead number two. Okay, lead number two is a little bit positive, but it's close to zero. Yes, it's close to zero. Oh boy. So this is -30, but because it's a little bit positive, we can subtract -10, so it means about -20 degrees. Okay, -20 degrees. It's meaning we do have a left deviation. Of course, it can be normal, but can be abnormal in this situation as well. Okay. Next one. Who has the next one? 106.
I do.
Okay. Do you want to share your screen?
No.
You are so brave. Okay. No. No.
It's arrhythmic.
Good. Very good.
So I took within 4 seconds, there were 10 R waves. So I multiplied by 15. It's 60 seconds and I got 150 beats per minute. So
Okay.
tachycardia.
Okay.
And for axis, I did the equiphasic approach.
Okay.
And both lead one and ABF were positive.
Okay.
So it would have normal axis.
Okay, but this is not an equiphasic approach. This is a quadratic approach. The equiphasic approach, if you want to use it, this is lead number 3. See? This is about the same. And this,
yes.
what you said, this is one positive AV, a positive, that's a normal. It's meaning that you are between 0 and 90 by looking at these two. However, if you are looking at lead number 3, okay, this is lead number 3 is equiphasic. It's meaning that this is exactly somewhere here. So 120, this is lead number 3, -90, that means about 30. Yes, about 30. So the axis is around 30. It's okay. It's still normal.
Yeah.
But if you had, now we can get a little bit polish it. If you had, for example, 30, it's meaning that the R or the positivity should be equal in lead number 1 and in lead number 2. But because lead number 1 is bigger than, see, it's a little bit bigger than lead number 2. This is why you are a little bit closer to lead number 1. So it's meaning around 20. Okay. Doesn't matter, it's still a normal one, but and for sure in your life you won't use it because the ECG gauge will write down exactly the axis. So you don't need to calculate it, but here you have to calculate it. Okay, let's move on. Next one, 107. Anybody? If not, I do it. As you see here, this is complete arrhythmia. And because there is no P wave, this we learn it on the next week. That's an atrial fibrillation. And we have to look at, for example, again, the longer interval, I get 1, 2, 3, 4, 5. So it has to be multiplied by 12. Okay, but which portion I should look at it? See, doesn't matter because if you, in atrial fibrillation, usually you have to take a longer interval, but let's use only this 5. 1, 2, 3, 4, 5, 6, 7. It means that 7, it's 14 and 84. Okay, but it's still in the normal range. Yes, it's 84. But if you count, for example, AVF is bradycardic, this is tachycardic. So usually atrial fibrillation is tachycardic and bradycardic syndrome, so it's changing the time all the way. Now, and the axis, let's see the axis. Well, it's very small, so it's low voltage that we do have. But as you see here, one positive, AVF positive, okay, that's in the normal range. And if I'm looking at, for example, which one should be equiphasic, maybe AVL, and if it's so, the axis should be 60. Okay, good. All right, let's move on. Okay, 108. Who has 108? Nobody. Okay, again, let's see. This is arrhythmic, okay? Now you can see that is changing a little bit, and especially the P wave, if you're looking at this is same, but here is not, okay? And this interval is shorter than this interval. We will learn it the next week that this some kind of early coming bit, so the premature bit. Because we do have arrhythmia, again, we have to look at a longer interval. Okay, let's see a longer interval. 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, and maybe it's 6 seconds. Okay, how many we have? 1, 2, 3, 4, 5, 6, 7, 8. So it's around 80 bit per minute. Fine. Axis. Now let's look at the axis. 1 is positive. Yep. AVF is positive. Yes. So it's meaning that we have a normal one. But let's look at again here. Which is the biggest one? Lead number 2, okay? And after lead number 3, and the smallest one, lead number 1, okay? So it's meaning that I draw it in the hexaaxial system again, okay? I'm drawing it. All right. So based on this, it looks like the axis is close to 60 because that's the biggest one. After 3 and after 1. So we have to come toward this one. For sure, a lead number 1 is still positive, so it meaning that you are somewhere here. Okay, somewhere here. You can say that maybe it's 70. The axis is around 70. Okay. Good. Let's move on. Number 9. 109.
Yeah, that's mine.
Good. You want to share your screen or not?
Unfortunately, I'm on my iPad.
You can share the iPad as well.
Yeah, I have the notes on the iPad, but I have the Zoom on my MacBook.
Ah, okay. You can share both if you want. Let's concentrate.
Maybe
Let's
next
see.
time.
Okay.
Yes, so it's not rhythmic. So for the heart rate, I used the lead 2 for 6 seconds and it covered 8 Rs. So it's 80 beats per minute, which is in the normal range. And for the heart axis, I'm not really sure. So maybe if you could explain that, that would be nice.
Okay. 1 positive. Yes. AVF is negative. Okay. So you cannot state that that's a normal axis, yes? Because what we do have here, okay, that's a hexaaxial system. We said lead number 1 was positive, so we are somewhere here, okay? AVF is negative, so we are here, okay? So far, yes? So you are on this quadrant, okay? Which lead that we have to look at now? Maybe I change the color. Yes, you have to look at lead number 2. Okay, lead number 2, because lead number 2 is perpendicular to AVL. Okay, that's minus 30. Okay, now let's look at lead number 2 is a little bit positive, yes? So it's not exactly minus 30, but it's a little bit less. So it's around minus 20.
Okay.
Okay.
Yes, thank you.
You're welcome. Okay, clear all drawing. 110.
That's mine.
Good. You want to share your screen?
I think we were two to prepare it.
Okay. Yeah.
So, what do you want?
She can share. I'm on my phone. I can't share my screen.
Let's do it.
Yeah, should I?
Yeah, go on.
Okay, because I don't know, because for me it looks kind of, so I don't know how to, I can say that it's kind of
Rhythmic or not?
It's
Yes,
rhythmic.
that's rhythmic. That's rhythmic. Very good. That's rhythmic. I think two of you got this one, yes?
Yes.
Okay, so you can agree or disagree and you can chat about it. Okay.
It's
So,
not it's not a normal rhythm because not every P wave leads to a QRS, but it is rhythmic because there's 11 boxes in between each QRS.
Okay, so that's bradycardic. It's very severe bradycardia. Okay.
Yeah.
We can calculate how much is it. Okay, let's start. 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds. How many you have? 1, 2, 3, about 30. So it's very low, the heart rate. Okay, go on.
And then the lead one is positive, so we know we're on the left side. Or
okay, so lead number 1, you say that's positive. Well, now it's about equiphasic. I would say this equiphasic because one thing, the first one, this is I draw it. Okay, this is the R and that's the S, a little bit wider than S than the R. Yes, so you have to add a little bit more to the S. This is S, and this is why it's equiphasic. So it's meaning that's 0.
Yeah.
Now you exactly what the axis is.
The axis is perpendicular to 1, and since AVF is positive, I'd say it's around 90 degrees.
That's it. Exactly. Yes. Because that's correct. Yes. Good. Very good. Okay. And you figured out very nicely that the P is not connected to the QRS complex. Next time we will learn it. That's a 3rd-degree AV block. But that's not the next time. That's 2 weeks from now. Okay. And that's looks like as a, not a ventricular rhythm, but as a low nodal rhythm that we do have. Okay. Good. Let's go to 111.
This is me. Hello, sir. I'm really sorry. I have my notes on paper and I didn't scan them in.
No, it's okay. It's okay. It doesn't matter. It's okay.
Okay.
You will learn sharing it because when you go to the 4th year and laboratory medicine, that's be online as well. So you have to learn by sharing your screen and presenting there.
Okay. So for this one, there is a regular rhythm. So I just used the 300-second rule to get the heart rate estimation.
Look at here that I drew.
Oh, wait, there it is.
See?
Yeah.
Okay, that's okay. So that's a rhythmic, but here we do have an early coming bit. So that's a premature bit. So it's not rhythmic, but you can say that it's sometimes we do have this extra bit when we do have, but I assume that, okay, it is rhythmic. Okay, good.
Oh,
Go
wait,
on.
sir. I think I did a different trace because my trace is different. Should I share my screen? I think I did a different one. So I'll do this one.
Yes, good. Do it.
Okay.
Oh, yeah, that's a hypertrophy, but doesn't matter. Doesn't matter. For practicing, it doesn't matter.
Okay, so for this one was regular. So I used the 300-second rule to calculate the heart rate, and I got around an estimation of 100 BPM because the R waves are roughly about 3 large squares apart. And so 100 BPM is still within the normal boundary, though it's borderline.
It's tachycardic. You can say it's tachycardic.
Okay, so yeah, you could say it's tachycardic. And then I did look at the intervals and I measured them because I wasn't sure if we were supposed to, and all of them were normal-ish. The QRS was about 0.08 seconds, which is normal. PR was like 0.12 seconds, which is also normal. And the ST segment in lead 3, well, at least the T wave is kind of missing. I don't see it here. I don't know what that means though.
Okay, we haven't studied yet, so you don't need to consider too much because you do have, okay, wait. You do have T waves. It's okay. You can assume that's
in
okay,
leads 1 and
especially in
2.
V1 and V2 and other. You do have, so it's no problem with that all.
Okay. And then for the electrical axis, I use the equiphasic method, but you can use quadrant as well. But I use equiphasic because lead 1 was equiphasic. And so I looked at what was perpendicular to lead 1, and that was AVF, and AVF has a positive deflection here. So you would say it's about like 90 degrees of an electrical axis, and that's within the normal boundary.
Correct.
And yeah, that's what I did.
Okay, very good, very good. Now, if we are thinking about that 90 degrees, okay, so we have to assume that lead number 2 and lead number 3 should be equal. Yes? And roughly about the same, yes?
Yeah, very roughly.
Okay, good.
Okay.
All right, we want to see it. Okay, we will go through. All right, first of all, rhythmic, yes. Heart rate, okay. 1, 2, 3, it's about 100. Good. We can say it's tachycardic, doesn't matter. Heart rate is 100. Okay, let's look at P wave. Yes, we do have P waves. Okay, so it's a sinus. So it looks like it's a sinus tachycardia. Next time we learn it. After we can use this quadratic approach, let's see, first of all, lead number 1 is negative, okay? AVF is positive, so for sure we do not have a normal axis, yes? We don't have a normal axis because we do have, okay, I drew this quadratic portion, we are somewhere here. Lead number 1 is negative, we are here, I'm sorry. Oh, no. Okay. So we are somewhere here. Because lead number 1 is negative, it meaning that we are somewhere here. AVF is positive, so we are here. Okay. Now, let's see what lead that we should look at to estimate the axis. That is, in this case, let's look at AVR. Okay. AVR. AVR exactly perpendicular to lead number 3. So it's meaning it's 120. Okay, let's look at AVR. AVR is negative, so we are somewhere here. So between 90 and 120. Okay, so you can assume that's a right deviation. Okay, clear? I assume if you are not saying anything, that should be understandable. Okay, good. Next one, 113.
Can you hear me?
Yes.
All right. Okay, first we saw it's arrhythmic. And we count in 3 seconds and also 6 seconds to calculate the heart rate. The heart rate between the 60 to 80 BPM.
The normal.
That's the normal, yeah. And the lead 1 is positive, and the AVF is negative. So it means the left axis deviations, and the lead 2 is almost 0 or slightly negative. But the AVR is negative, so
it doesn't matter AVR. It's okay. Okay, good.
Range between the -30 to -60, I think, maybe -45 degrees.
Okay, that's okay. So a little bit less. So you can say it's a -40. Doesn't matter. That's good. Now what you did is very nicely because AVR exactly perpendicular to -60. Yes, this is what you did very nicely. So somehow it's falling between -30 and -60, but because it's closer to, because lead number 2 is almost equiphasic, so it's close to -30, so you can see it's -40. That's correct. So that's a extreme left deviation or pathological left deviation. Correct. Good. Okay, good. Let's move on. 114. Anybody? Okay, let's go. That's rhythmic. Heart rate is tachycardic. It's less than 3. We're close to 3, so it's around 110. So for sure it's tachycardic. But we can guess nicer. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 12 times 9. That should be 108. Yes? So it's 110. It should be fine. So it's tachycardic. We do have P waves, so it's a sinus tachycardia. Let's look at the axis. Lead number 1 is negative. AVF is positive. So for sure it's not normal because that is located somewhere here. Yes, somewhere here. Because 1 is negative. Okay. AVF is positive. So we are here. Next one that we have to look at, AVR. AVR is right here, perpendicular to 120. So it meaning that that's a extreme right deviation. Yes? Yes. Okay, next one, 115. Anybody? Nope.
Hello, it's mine.
Good. Can you share your screen or you want to present here?
Unfortunately not.
Okay, good. Say it.
Actually the heart rate is around 75 beats per
Rhythmic
minute.
or not? Rhythmic or not?
It is actually normal sinus rhythm because each QRS is preceded by a P wave, and the P wave operate in lead 2 and AVF. And also about the deviation, lead 1 actually is negative, and the lead AVF is positive. I think we have the right axis deviation, axis between positive 90 degree and 180 degree.
Okay, but because I showed you that AVR, that exactly perpendicular to 120, that's about 0. So again, we do have a extreme right deviation, 120.
Yes.
Yes?
Yes.
Okay, good. All right. Next one, 116. Anybody? Nope. Okay. Rhythmic. Okay, very good. The heart rate is around a little bit less than 100, so it's about 90. P wave, yeah, we do have P waves. Okay, we do have P wave in front of lead number 2. Best one, look at it, for example, the chest leads, V1, V2, V3. Yes, we do have P waves. Axis positive in lead number 1. AVF is positive because it's an abnormality. That's an ST segment is elevated, but this we have a positive R wave, so that's normal. All right, we can say it's normal. And when you are looking at here, the perpendicular one, exactly the negativity, positivity, the same in lead number 3, so it has to be around 30. Okay, I will show you again. Okay, lead number 1 is positive. We are here. Good. AVF is positive. So we are somewhere here. Lead number 3, this is what we have to look at right here. That's about equiphasic. And this is what we do have here. And however, if you want to consider that if you had, for example, 30, it's meaning that the 2 and the 1 should be equal, but it's closer to lead number 1. So I would say maybe 20 degree, but it's still a normal one. Okay, good. 17?
Hi, yeah, that's mine.
Okay. You want to share it or you want to present here?
I'll present here.
Okay, good.
So I can see that it's arrhythmic.
Mm-hmm.
And for the heart rate, I calculated within 5 seconds. So I saw 6 beats. So it was 90s.
Mm-hmm.
And for the axis, I used the quadrant approach.
Mm-hmm.
And lead 1 is positive, and AVF is mostly negative.
It's about equiphasic, but close to zero. Now, this is a little bit changing. Okay, here, for example, is negative.
Mm-hmm.
Here is negative, but here a little bit maybe equiphasic or maybe positive.
Mm-hmm.
Because when you breathe, the diaphragm is pushing up and down, so moving the axis of the heart. So I would say that AVF is zero. Okay, I would assume that that's a zero. So the AVF is zero, the axis exactly lead number 1, that is
A0.
exactly. This is what you can see. Okay,
Okay.
good. Oh, okay, I stop recording.